Okay, so as next, I would like to spend a few minutes to show you a simple example about the primitive joints. And the example that I would like to introduce you is the one you can see in this slide. Let me change the view for you guys. So this one. So I have a very simple system that consists of one moving body only. And the one moving body is constrained to ground by using two primitive joints. And these two primitive joints are located in a place or points that are called P, that is here, and O, that is here. The P is from the distance, okay, maybe better to get started from the O. So the O is from the distance D along the global x-axis. So this distance is D. The P is the distance E from the global y-axis. So those are the distances where those slots are located. And I would like to create the primitive joints for this system. And now when you look at the system, you can already compute the number of degrees of freedom. And the number of degrees of freedom will be 1. And it will be 1 because I have one moving body. So it's going to be 3 trenorized coordinates. And then I have 1 plus 1 primitive joints. So that's going to be 2. So it's a total of 1. So the system can move one way only. And the way it can move is like, you made the picture by yourself. So it's like sliding in a way that is like a pendulum a little bit. Little hard to describe here, but it's going along these slots, and that's how it behaves. So that's the simple mechanism. All right. Any ideas how we can describe these constraints? We will use, surprising enough, the equation that is written like this. Okay, so that's the concept again. What we're going to do with this concept? We will define the points. First, we're going to define the point O, or point P, doesn't really matter, by first traveling the body, or the origin of the body reference coordinate system, and then with help of the U-bar, we're going to reach one of the ends of the beam-like body. And once we reach the end, then we're ready to impose the constraint. And the constraint will be very simple. So we're saying that this particular location must have global x position that always have to be equal to D. That's the idea. In the similar way, we're going to travel to this end. We say that the global y direction of point B always have to be E. That's how it goes. All right? So let's see. So let's get started from the point O. So point O, we will use this equation. So first, again, we have this R vector that tells how is a translation of the body reference coordinate system. All right? So it takes us from here to here. And then we're going to use a rotation matrix to describe the orientation of the body. All right? And then we're going to use a vector U bar to travel from this coordinate system to this point. So if the length of the beam-like body is L, so how is that I can reach this end? Well, you can tell it here. So the components of vector U bar, the x component must be L divided by 2. Think about it. You here, you have to travel here to here. So the distance will be L divided by 2. And how much you have to travel to this direction? 0. Okay. So this is my equation. So now the next assignment is to impose the constraint. You have to understand that this equation here tells me how is a point O with respect to global coordinate system. So I'm ready to assign my constraint, and the constraint is that this x coordinates always have to be equal to D. How can I do it? I simply say that x have to be equal to D. All right, makes sense. Make sense? No. Would you like me to repeat it? Okay. So let's first look at the big picture again. Big picture is this. My point O is constrained. And the point O is constrained in such the way that it can do everything it wants, except it cannot translate along the global x-axis. This motion is not possible. It is constrained. And this is exactly what I wanted to constrain. So I wanted to express the position of this point using the equation that I'm very much familiar with. And then I'm going to take up, because this one here consists of two components that are with respect to global x and global y directions. Now I'm going to take and say that the x direction is no longer free to move, but instead it always has to have the value equal to d. Make sense? Okay, so I'm saying, okay, this is my position, and this motion is no longer possible because the coordinate x must have the value d, no matter what. How can I make it happen? I can make it happen by expressing first this translation. Well, it's a variable, so I really don't know what are the numerical values. I don't really care about that. So there are rx and ry. So translation along the global x and y direction. All right? Then I have 2 by 2 rotation matrix that accounts the orientation of the body reference coordinate system. All right? So I'm traveling here. I'm accounting the rotations. And then I'm traveling here with help of vector u bar. Vector u bar have a value of L divided by 2 and 0. You're doing this, or okay, what is your sign to me? Please communicate with our own special language. Okay, what is your sign? So it's clear. Okay? So okay, that's my definition. And now this tells me the position O in x and y direction with respect to global coordinate system. All right? So now I'm saying that this x here is actually predefined. X is predefined to be equal to d. That's my constraint, except that it's not yet my constraint. I still need to do the math. So I have to compute, I need to take this Rx. I have to compute this matrix multiplied by this vector, but it's going to be this row. So it's L multiplied by cosine theta. Then this is 0. And then d, I'm going to take it and put it in the left-hand side of the equation. This is my first constraint. Clear? One constraint equation, which eliminates the motion of this point in global x direction. It cannot do that any longer. It always has to stay in a coordinate equal to d. Okay. Clear? Are you guys depressed? Not at all. Is this too simple? A little bit. But no worries, because soon it's going to be difficult like in hell. I can tell you that. All right? So that's the first one. But not today. It's not going to be today, but within a week or two, it's going to be like something that is hard to stand with. All right? What about the P? Any ideas how we can proceed with the P? Same procedure. We always following the same procedure. So basically, we always keep on repeating this equation over and over again until you get bored. And then still we're going to repeat it. So it's repeating. Okay, this time the assignment is to go to this point here. How we can make it happen? Well, first we go the body reference coordinate system. It's going to be business as usual, so no differences there. Then we're going to account the body orientation. No differences whatsoever. It's going to be exactly the same that in the previous case. But then there's going to be vector u bar. Vector u bar must be different because I'm not going to go here, but instead I'm going to go here. How is that I can make that happen? I have to travel to minus x direction. How much? How much? L divided by 2. How much I need to travel to y direction? 0. So that's my vector u bar. And then I'm going to go and introduce the constraint. This time the constraint is imposed to global y direction. The y direction is no longer free to move, but instead it has to have a certain value. The value is defined here. So then I do the math. I will take this time this component here, this row multiplied by this vector, and then I'll take an e and put it in the left hand side of the equation. Here's my second constraint equation. Simple. Make sense? Yes, sir. Okay, so this one was the problem. Negative. Okay, that's because, you know, if you take a close look about the axis, coordinate axis, you know, my x-axis, positive direction, is pointing this direction. So I'm not going to go the positive direction. I need to go this direction. This is a positive direction. I don't want to go there, but I want to go here. How can I go there? Minus L divided by 2. Okay. So, clear. So that's a simple primitive joint. All right? What is the purpose of the constraint equations? What's the nature of constraint equations? Here are the 4 choices. It interconnects, it combines generalized coordinates. It defines the body configuration in global coordinate system. It defines the physical dimension of the body. It defines a particle in a global coordinate system. One only is correct. What is that the constraint equations are doing for us mathematically? Joints. What is that they do? And let me change the view to this one. Okay, so is this going to be simple or what? Quite simple. Would you like to have a word with your fellow student? No, no need. So you're absolutely positively sure what's the correct answer? Okay, so maybe I will let you, would you like to think about this, or I'm not really sure what is that you're thinking. It's very hard to read your mind. Are you like, oh my God, this is, this is like a nightmare? Are you thinking that this is so simple that I will fall asleep, or tell me, what are your thoughts?